In this lab, we'll be using calculations from Lab 1 and producing a computational model of two charged tapes exerting an electric force on each other. We will use this model to estimate the amount of charge in each tape necessary to float one above the other. Unlike Lab 1, we will distribute the charge evenly across the length of tape in our computational model and not concentrate on the charge at a single point. Therefore, we can compare our results from Lab 1 and Lab 2 to see which one is more accurate and why. Here is the data from Lab 1 and Lab 2 shown. The length of the tape, mass of the tape, and the distance between the tapes are all the same. However, the magnitude of gravitational force and electrical force, as well as the charge in both labs, are different. The charge from Lab 1 is more than 3 times less than the charge from Lab 2. The magnitude of gravitational force and electrical force from Lab 1 is a little smaller than the one from Lab 2. Here is the code from Lab 1. You can see, I will explain it more in detail in the previous video if you want to go check that one out. But here, I'm just showing that, as you can see, the gravitational force and the electrical force are both equal but opposite, because in order for the top tape to float, these magnitudes have to be the same. Here is a code from Lab 2. As at point 35, where the arrow is shown, I used the same code from Lab 1 to calculate the electric field. So basically it's saying the R vector is equal to the observation location minus the charge particle position. R mag is square root of x value plus y value plus the z value. And then R hat is R vector divided by the magnitude of the R vector. And of course, the electric field is 9 times 10 to the 9th times the charge over R mag squared times R hat. So basically 35 to 40 is just calculating the electric field. At line 48, I didn't edit these lines. This was given to us, but in short, this is just creating the line charges. So basically taking a bunch of point charges, taking the line and dividing it by a bunch of singular point charges and distributing the total charge throughout each one. At line 79 and 80, I am creating the top tape and the bottom tape. So as you can see at where it says start position equals vector, for the top tape, I'm using that as my origin, and the bottom tape is 0, negative d, 0. D is the distance between the tapes, and that's in the y position as well. N represents how many points I am using. So how many times am I splitting that tape up to calculate the electric field at each point. So the more times I split it up, so the higher that N value, the more accurate of a calculation I will get. So the top tape is red and the bottom tape is blue, which you'll see in the next slide. So if you look to the right, this is my my model that was rendered. The top tape is in red and the bottom tape is in blue. The green arrows, which are really small because it's 100 of them, and it looks like a little like grass in a way. Those are the singular electric fields being calculated, which I'm about to go over. So where the arrow is pointing at point 110, this is where I am starting my loop to iterate through each piece of charge and the top tape. So at 111, I am creating the vector the electric field for at the top tape. And in the next line, I am creating the arrows. So here, this is where I start calculating the electric field at the location of the top tape from the bottom tape. So I stated before that E-field code that I was using in the beginning, this is being put into work at this location right here. So after I calculate that electric field, I then add it to the vector that we created before in the previous slide, because we need vectors to continue our calculations below, where we're about to go over right now. So to calculate the electric force on the top due to the bottom, I'm going to need that electric field that I just calculated in the previous slide. And then I multiply that by the charge, and that will give me the force. So once I have that force, I then add it to the vector which we created at line 105 to make that a vector as well. Because in my calculations, when I multiply that by a number like the singular charge, it creates a scalar, so I have to convert that back to a vector. So down here, line 134 and 135, this is where I'm creating the arrows that you see off to the side, the white and the yellow one. This is the total electrical force, the magnitude of electrical force and the magnitude of the gravitational force. So in the beginning, I was talking about how the charges were different. Initially, I inputted the charge from lab 1 that we calculated into this code. However, when I do that, the gravitational force did not match the electrical force. So I had to edit that charge manually until both arrows were equal but opposite. And that's how I came up with the charge 1.739 times 10 to the negative E coulombs to balance them out.